It's time for Alfa Laval. As you can see, we're a couple minutes late. Before I let go of the microphone, I do have to thank Northwest Food Processors Association. They have been our convener for these food processing innovation showcases for the past 18 months, and we benefit greatly from the way they manage their members. They have multiple standing committees for food safety, for production, for energy, for sustainability, and we have the full run of those committees to ask what is the biggest problem that you all have, that you all know, that you all have to solve, that you're willing to talk about in the open. And that's really the genesis of where these topics come from. As I said before, we do want to hear from you folks out there what you want to hear about, and the evaluation is coming up and you can tell us all about it. Another point about NWFPA, they've taken a really bold step to say they want to reduce overall energy intensity by 50% in 20 years. That means get double the work for the same amount of energy. And so this moving less water business has a lot to do with turning pumps less along moving to that outcome. Also want to give a quick advertisement for ourselves. March 31st is our next innovation showcase. This one is on waste heat recovery, on a new method of getting chilling out of not boiling waste streams. Some really, really exciting stuff has come online that you'll want to hear about, March 31st. And so, gentlemen, it's time for you. I'm going to get off the phone and take it away.
Okay, thank you. First of all, just to explain that both myself and Ben will be doing a joint presentation here on behalf of Alfa Laval. And again, I would like to say thank you for the invitation and also for the time from the participants today for spending time with us. My section will be on a focus of recovering processed water prior to going to wastewater treatment. And the main idea around there, as you've already heard, is to use something called reverse osmosis to essentially remove dissolved solids. Ben's section will be on our membrane bioreactor technology, which will be part of a wastewater treatment plant. And Ben will discuss some of the innovative new ideas that we've come together with from Alfa Laval. Before I get into the actual process examples, I would just like to give a bit of background to the membrane section of Alfa Laval. We actually started up just before osmotics. In fact, in 1965, we were one of the first pioneers to bring membrane technology modules and systems to the world. At that time, it was well before spiral technology was available. It was plate and frame technology. And in fact, we became part of Dow Chemical Company. We were the European manufacturing headquarters for Dow during 1989 to 1997. And in fact, it was in 2002 when we were acquired by Alfa Laval. And today we are the business center for membranes within Alfa Laval technology.
And Gary, I'd also like to mention that Alfa Laval is the largest membrane manufacturer in Europe today.
Absolutely, Ben. Yes, exactly. And you know, in fact we've seen tremendous growth over the last few years with Alfa Laval in terms of our production, and certainly we're moving towards in excess of 500,000 square meters per year of membrane production. So what do we do? I thank Cliff for this because he's already introduced the concept of microfiltration, ultrafiltration, nanofiltration, and reverse osmosis. I'm not going into the detail of that with this presentation, but I just want to point out that we do actually produce our own membranes. This is one of our two membrane casting machines. We also, having produced the flat sheet membranes, today we have a large focus on converting those flat sheets into a spiral element, and we have our own production system in place in Denmark for producing the spiral elements. And of course the key feature with spirals today, as many of you may know, is that it's one of the most cost-effective solutions for membrane technology. We actually focus, a lot of our business area is not just on, let's say, wastewater side or process water recovery, but generally working with customers and their processes, working with their products. So we have a big focus on full-fit sanitary design type membrane elements, and our elements are UF, RO, and NF membranes, spiral elements are USDA compliant. Just to recall, the first modules we produced were actually, this was back in the 60s, were something called plate and frame modules. We still use these today. And in fact, this will be where we're working with streams that contain essentially more suspended solids and also high viscosity operation. So this is still an option available to us. These are the membrane bioreactor modules which Ben will cover, and this is for the wastewater treatment plant installations. And what we have as part of our portfolio, of course, once we have the correct module for a particular application, then we can look to build in other Alfa Laval components such as pumps, valves, heat exchangers, and combine that all into a skid-mounted unit, which could either be a plate and frame system or alternatively the more cost-effective spiral system. And we also always like to mention that since our beginning in 1965, we've got more than 2,000 installations worldwide. I think in the early introductions, one of the questions was, what's new? And what I would like to say here is that certainly what we've been looking to develop since our introduction into the Alfa Laval group of companies is how we can combine membrane technology with other separation technologies like high-speed separators, decanter centrifuges, heat transfer equipment, which is essentially plate evaporators, and looking for the most cost-effective process solution. That could be in terms of reduced energy consumption, reduced capital cost, of course, but also environmental impact. So we're working towards being able to recover water and give a much more environmentally friendly solution whilst maintaining low-cost production. One example I'll just bring up, and I haven't intended to mention this, but just with the introductions, I can say when it comes to oily wastewater, this is an area of interest for us because we actually now have two examples been running for about 5 years in Scandinavia, where we have a combination of high-speed separators, decanter centrifuges to remove free oil, and then we bring in a special type of ultrafiltration membrane which is very good at handling emulsified oil, and that can reduce emissions down to less than 1 to 2 parts per million. This is something that we're working with more in the oil industry rather than the food industry. So the example I want to consider today, and this is just one of many, but this is something that we've been working with the baker's yeast industry and producers. And this was a start because we realized that baker's yeast producers generally are working with high water volumes, and as a consequence of producing high wastewater volumes. And because of the new environmental demands, we saw some years ago that there was a much greater focus in these companies for water management. So the solution we have here, and this is the solution I want to talk about, is by using reverse osmosis, we can actually see ways of recovering water for reuse. And of course, as a consequence, that reduces the site water usage coming in and also the site water volumes going out in terms of emissions. So just as a recap to what Cliff said earlier, reverse osmosis, primarily we are saying that only water will pass. I should stress, however, that there is one or some small organic components that can also pass with the water through an RO membrane. One primarily would be alcohol. Another one could be something like acetic acid. And in that case, we will often look at a pH adjustment so that we can get a higher capture, a higher retention or removal of acetic acid, which tends to precipitate out at neutral conditions, sodium acetate. But essentially, and I think again Cliff mentioned this, when we talk about reverse osmosis, we define this as being a very tight membrane which will remove at least 97% of dissolved salts. But I have a small animation here which, if I can just run that, Andy, thank you. And I'm not seeing it, there we go. Apart from the smaller salt molecules, you'll see that reverse osmosis will also retain larger molecules like sugar molecules, protein molecules, amino acids. Many of these larger groups will also be retained. So, you know, depending on what process application we're working with, we can be sure that reverse osmosis is going to primarily remove all those molecules and only leave us with the water.
Hey Gary, pardon me, I'm sorry to jump in, but that video, I didn't see it, and I have several monitors in front of me, and we didn't see it. So Andy, can you kick that again and see whether we can see it? We got a black screen. It looked like it was sharing, but it didn't render.
Thank you, Steve. I actually have the...
There it is. Go ahead.
Yeah. So yeah, you know, this is just a very brief, simple animation, just showing that apart from the yellow molecules, which would be the salt molecules in this case, we're also retaining other larger molecules as well. So as long as we're talking dissolved solids, then, you know, reverse osmosis will essentially retain and remove everything and leaving essentially clean water to pass through the membrane. Thanks for pointing that out, Skip. And if we think about that, if we think about our water removal, another method, of course, is to use evaporation. And evaporation is very good, especially with the plate evaporators, which we do at Alfa Laval. I know my colleagues would say that we have a very efficient method of water removal with plate evaporators. But however, with evaporation, you have to undergo a phase change, and that involves additional energy. In our case, we're not converting water into steam, and this gives us a more efficient method of water removal, and can potentially give up to 40% savings in running costs, which is what we've seen in some good examples. So when it comes to the reverse osmosis systems that we work with, we are actually, again, offering a skid-mounted solution. So these are very easy to fit on an existing site. It's relatively small footprint. They're generally modular and can be expandable for future expansion in process flow rates. If we look at the typical baker's yeast process, this is the overview here. Our focus is not on the production of the yeast itself, which is normally separated by the high-speed separators after fermentation, but we're actually looking at this area, which is essentially the waste streams coming from the high-speed separators. And there's two waste streams that we can consider. There is the standard light phase coming from the high-speed separators, but there's also a spent wash water phase, which I'm just trying to get an arrow here, pointer, it's not working for some reason, bear with me, here we go. So as part of this separation, we have to introduce wash water into the high-speed separators, and so we get a secondary light phase, if I call it, stream coming out of the separators. And this example I'm showing is where we actually looked to combine those two streams and feed them into an RO plant ahead of the existing evaporator. So to put some figures on those streams, typical capacities would be between 40 to 80 cubic meters an hour, and I'm sorry for the European units, I've also translated them to gallons per minute. And in this example, we would be looking to do somewhere between a 1.5 to 2 times concentration. This gives us 33 to 50% water recovery. Something else that was pointed out earlier is with reverse osmosis, we have to be able to pause the production process typically for 2 to 4 hours every 24 hours day period. And to allow us to do that, we will often consider a special design system which allows us to do what we call sequential cleaning of individual loops in the system, which allows the plant to run for 24 hours per day. Typical energy consumption is around 6 to 8 kilowatts per cubic meter of water recovered, or between 0.023 and 0.03 kilowatts per gallon. We also have another opportunity to bring in reverse osmosis, and this is actually after the evaporator. The condensate itself can also be a pollution problem, and if we look at that, we can also look at doing a reduction, a concentration, and in this case, feed capacities could be anywhere between 50 to 100 cubic meters per hour. We can do 10 to 20 times concentration, which means we can typically recover in excess of 90% of the feed as pure water for reuse. And again, as before, we can consider a continuous reverse osmosis running system. Because of the evaporated condensate generally is a little cleaner than the earlier stream, and this allows us to run with slightly more efficiency on the system, 4 to 6 kilowatts per cubic meter of water recovered. I've just combined this as a final summary in terms of flows. You can see here that we've got the two light phases coming together. This was an example we did for a project in Asia, and we had, and I'm sorry for the metric units, but we had totally 120 cubic meters per hour of water going into the RO plant. With a 2 times concentration, it gives us a water recovery with a COD level of less than 500 ppm at 60 cubic meters per hour. And then if we look at what we can also pull off the condensate, we have an additional 40.5 cubic meters an hour water recovery. So of the 120 going in, we're actually able to recover water of more than 100 cubic meters per hour. And I point out that COD levels here are shown as typically less than 500 ppm. We can, by doing a double pass on the RO system, reduce that further down to potentially less than 200 ppm. That's COD. So to summarize, with the RO technology, one of our main features, we're offering sanitary RO membrane solutions. It's not just standard water elements. Of course, we have to, I haven't explained that, but with sanitary RO membrane solutions, we offer full fit sanitary elements, which essentially allows and promotes the flow of liquid through the module, so we don't get any stagnation or dead legs or dead flow periods, and this ensures that we don't get any microbiological activity in the process. As I've already shown, we can expect to get over a 90% clean process water recovery for reuse prior to the wastewater treatment plant. And of course, ultimately that gives us savings in process water consumption and water disposal costs. Now I'm going to hand over to Ben, who will take us into the next step, which would be to take that concentrated streams that we've taken from our RO systems, and we're now feeding that into the wastewater treatment plants, where Ben will look after the membrane bioreactor principles.
Thank you, Gary. As Gary mentioned, we're now going to talk about the membrane bioreactor technology. I think that the first thing I wanted to very briefly discuss is that I work with the process water and wastewater group for Alfa Laval, and we have sludge solutions, and we also have wastewater process solutions. On the sludge side, we have thickening and dewatering with belt presses and centrifuges and screw presses, and we also have heat exchangers for sludge heating. And on the wastewater process side, membrane bioreactors, tertiary cloth media filters, sequential batch reactors, and aeration systems. And what we're going to focus on today is the membrane bioreactor technology. I think the first thing that we really need to ask ourselves is, why would we even use a membrane bioreactor? So I've come up with a few reasons here that I think most people would agree with. It is truly a one-step biological wastewater treatment and membrane filtration process. This makes it have a very compact footprint, and it also produces reused quality water in one simple step. This reused quality water can be used for irrigation, or cooling towers, or it's actually ready for RO feed water.
That's right, Ben. I mean, just to point out, that's where the benefit is here, that it would remove the suspended solids and give us cleaner water going into the RO, so we don't get any premature fouling of the RO membranes.
That's exactly right. So if the facility does want to run reverse osmosis, you can go from your wastewater to the MBR to the RO, and you are good to go. It also will reduce your fresh water and sewerage cost if you reuse that water. If you want to retrofit an existing activated sludge plant with membrane bioreactor technology, you can, let's say, get approximately twice the flow capacity out of that plant if you go to the membrane bioreactor. So it's also a good retrofit option. And from an effluent quality standpoint, it meets future needs and also current needs. So those are what I see. That's what I see as the main reasons to buy the MBR. We are focusing on the food and beverage market. If you look at the entire industrial MBR market for the United States, the food and beverage portion is about 26% of the total market. And then if you look at the preference for flat sheet versus hollow fiber membranes, hollow fiber membranes are a more traditional product. Flat sheet is a bit newer, but the industrial market preference for the flat sheet membrane is definitely increasing, and the hollow fiber preference is flat or perhaps going down. The effluent quality that you get from the membrane bioreactor is really one thing that sets it apart. From the membrane filtration standpoint, you're going to get less than 3 ppm of total suspended solids, turbidity less than 0.5 NTU, and you're also going to get a multi-log reduction of both bacteria and viruses. From the biological process perspective, BOD, or biochemical oxygen demand, is typically going to be less than 5 parts per million, and COD, nitrogen, and phosphorus numbers coming out of the MBR are really going to be based upon the biological wastewater design. If you look at traditional MBRs essentially replaced a gravity process for liquid-solid separation, which is a clarifier. This was replaced by large pumps and much more intensive screening. A typical wastewater plant now may have a 6-millimeter screen, and a traditional MBR has to have between 0.5 and 2 millimeter screening. So you've added a lot of mechanical complexity to the process as opposed to conventional activated sludge. Well, what if you could eliminate a lot of that complexity and kind of go back to a gravity-driven process, which is exactly what Alfa Laval has done. We do not need pumps for permeation, and we only need a one-stage screening up front, around a 3-millimeter screen. And we also do not need multi-Q mixed liquor recirculation pumps. If you look at what the competitors do, they have to have a multi-Q mixed liquor pump that will pump from the membrane chamber to the aeration chamber to try to equalize the mixed liquor concentration in the two. We can go ahead and go to that animation. Thank you very much, Andy. If you look at this animation, what we do is we have an air scour, which all MBRs do, and the air scour in our particular case creates an airlift in the membrane module, and we harness that airlift, and we have ports at the top and the bottom of the tank. We harness that airlift and we create the mixed liquor recirculation necessary to equalize the mixed liquor concentration. And we can go back to the normal slide. Thank you. There we go. So we effectively can get up to 8Q mixed liquor recirculation without recirculation pumps at all. The key features really and the benefits of the Alfa Laval MBR are the direct result of a very ultra-low pressure drop membrane bioreactor technology. We can operate our MBR in 4 to 16 inches of water. That's all it requires. And that enables us to do gravity operation, which is going to save you a lot of capital maintenance and energy costs. We don't need permeate pumps. We do not need backflush pumps either, and we don't need mixed liquor recirculation pumps. The other effect of the ultra-low pressure drop is we have very, very low fouling rates, so we can save up to 70% on membrane cleaning costs. In other words, much less chemical consumption, much less labor costs. Also, our membrane modules are not required to be periodically lifted out of the tank and manually cleaned. We also do not require separate soaking and cleaning tanks. And then if you look at the labor and chemicals associated with membrane maintenance, we have reduced safety, health, and environmental costs. As far as our module construction goes, we have a PVDF membrane which is bonded to a hollow core polypropylene panel. And the hollow core panel is the permeate carrier. The PVDF membrane is bonded to both sides of that polypropylene plate, and then we stack the plates together and we form what we call a cassette. And each cassette is approximately 3 feet by 3 feet by 3 feet in dimension. And then we stack the cassettes 1, 2, or 3 high, and depending on the flow rate that you want and the depth of your tanks. One thing I do want to point out here is that if you look at the permeate ports on the module, we collect permeate from all depths of the membrane itself, so we have very even flux distribution across the membrane surface. And then we also have air scour manifold at the bottom for air scouring. Go ahead and roll the next video. Thank you. If you look at this animation, this is our primary mode. The mode is permeation. We permeate for 10 minutes, and we control the permeation through an effluent valve. That valve is controlled by a pressure transducer in the aeration tank. So what we try to do is maintain the aeration tank level even, and then vary the flow of the permeate. That's fine on that slide. Thank you.
Hey there, Ben.
Yes.
You probably noticed that the panel and I are on the line. Just it's
Yes.
5 minutes before the hour. We want to make sure that there's time for questions. So, can you wrap in a minute or two?
I can do it in 1 minute.
You're the man. Go for it.
All right. Next animation, please. And the next operating mode that we have is our relaxation mode. And all we do is we stop the permeation with our relaxation valve, and that converts the transmembrane pressure drop to 0, and so we're able to scour off any suspended solids that were clinging to the membrane surface, even with an ultra-low TMP. And we do not need backflush pumps. We don't have a backflush mode. All we have to do is stop permeation. Okay, back to the slide presentation. Okay. Essentially the last slide. I'll get it done quick. Let's go to the animation. Since we do have such low fouling rates, we typically only have to clean 4 to 6 times a year. The most common cleaning chemical is sodium hypochlorite at 500 ppm. In this case, we actually recirculate the cleaning chemical in the plate and slowly through the membrane, so we get an extremely efficient cleaning of the entire membrane surface. And this is where we can save up to 70% on cost for maintenance, because we just don't need to clean very often. Back to the presentation. Skip, I think yeah.
Yes. Okay. So Gary, Dan, Ben, thanks so very much. And so some quick housekeeping. Here's what we're going to do. We want to make our commitment of getting people on and off within the 2 hours, but we can stick around and answer questions after the top of the hour. So I do need to. First off, I want to say it's great that I don't have to pump for questions, because this audience has been very active in chat, talking with each other. I also want to ask your indulgence, audience, to please give us your feedback. There should be showing up quickly a URL which is active in chat, and that would be an evaluation where you can tell us what you liked and didn't like, and what you want to see more of, and what we should do for other topics. Your input is really, really valuable, and it's a disaster if we don't have it, because we need to be relevant to what you guys need. I do want to say thanks again to our panelists, and I want to jump. We will actually just open up for questions right now. How we doing, panel, at covering the breadth of the marketplace in general, and then let's come back to questions for Ben and Gary specifically. How do you think we did?
Well, I think the GE presentation helped with an overall review of what the waste treatment process is about, and then the GEM is a good pre-screening tool before you go to an RO-type membrane bioreactor. So I think we covered the bases pretty well.
Yeah, I support what Sam just said. So
excellent.
We covered it pretty well. The oil and grease, TSS, and all three presentations did a nice job.
Perfect. Okay, well, let's take some questions. And Dan and Sam, you've done a wonderful job of scanning the chat. So why don't you act as proxy for the audience and ask a few questions?
Well, one of the questions was related to the energy units that were cited in the energy use in terms of the RO systems at Alfa Laval. Was it kilowatts per hour per gallon or per cubic meter?
Yeah, it's kilowatts per cubic meter of water recovered based on pump energy consumption.
When you have that accent, you can only think in cubic meters.
Yeah.
I do apologize for that, yes, indeed.
I wish we all could work in cubic meters. It would be so much simpler.
That's why I always use convert exe to convert things.
Did you say you were working in qubits?
Yeah, that's right. Yeah, that's the old one. Yes.
I
I will apologize. I've been now based in America. You know, I'm still part of our central group in Denmark, but I'm sitting now here in Richmond, Virginia. Even though I'm English, and I did have a head start compared to my European counterparts. It's a struggle to get back to the old imperial units, but I'm working on it.
I just want to say that I appreciate being on the panel because it allowed me to see directly the Alfa Laval process for the MBR, which has a new twist on it for things that I've been familiar with in the past. You know, the high pressure hollow tube membranes, the flat plate membranes, but this one adds a new twist to the quiver of what MBRs can do.
Yeah.
And how does the energy consumption of a Alfa Laval MBR compare to your typical MBR that requires a backflush and pumping?
Yeah, that's a really good question. The energy consumption is comprised of a lot of different things, and especially if you use our triple module, which only requires 1/3 the air of the single module, the energy consumption of our MBR is similar to the traditional membrane bioreactors. And we're working on improving that all the time.
So is that because instead of a pump, you've got a water pump, you've got an air pump?
No, we don't. Well, I mean, we're going to use the air scour regardless. So we just decided to harness that blower energy. But I mean, it's pumping energy and it's air scour, and then it's aeration of your biological process. That's all of the electrical consumption And when you take all that into account and you look at our triple stack membrane, it will be similar to the traditional technology.
Okay, thank you.
So, Dan, in our case, we're considering this kind of technology as a final tertiary filtration process, but what we could do in this case is simply insert these modules into our existing aeration basin and reduce a lot of capital costs for not building a new unit operation. We just insert these modules into our existing aeration basin.
Yeah, and since it operates by gravity, it's very easy to control with that permeate control valve.
Right.
Very simple control system.
So I'm glad I'm on the panel.
And you are too.
Does he get a discount?
We'll have to talk about that.
It was a cheesy question.
Thank you.
A little bit cheesy.
We'll provide you with some ice cream. How's that?
I'll see you. I'll see you this afternoon.
Please do.
Okay, any other questions for these fine gentlemen?
Nothing in particular. There was nothing popped up besides those energy units and my question about energy consumption.
Well, Sam and Dan, I really want to thank you for participating in this. You kept it sprightly for us and made a big contribution. I appreciate it. I also want to mention my partners off screen here at ATA. We have Andy and Ron and Laura, who I don't give enough credit to, and our partners over at OMEP, particularly Linda and Jasmine. Thank you, guys. It takes a lot of energy to put this whole thing together. And thank you to the panel and the presenters for all the preparation that went into this. So, oh yeah, the other thing to say is that all of this is archived, the videos and a whole bunch of cool content, the surveys that you answered, all that information will be archived and available probably by the end of the day on Friday on our website. I don't have a posting of our website here, but it's simple. It's emergingtechaccelerator.com or etaccelerator.com. So, any final word from the panel or Ben and Gary?
Thank you, Skip. Thank you, Andy.
Just to say thank you.
Yep.
A great way to sign off. Thanks, gentlemen, and have a great
Thanks,
afternoon.
everybody.
Thank
you.
People that listen, thank you very much.
Yes.
Yep.
Bye-bye.
Bye.